right, what do we get for the first one? -4. And the last one? +1. Okay, so we just fill in the value that they're asking me to evaluate for x, pull it from the table, and then do what it says. Okay, like those a lot. Right. All right, so let's take a look at all of these learning targets today. There are 5, but I want you to notice that what they all kind of work around. Identifying an appropriate function type, describing assumptions and restrictions related to a real-life function model, okay? If we're building a house, the height can't be 0 or it can't be negative, that kind of thing. Constructing linear, quadratic, cubic, or any polynomial, or possibly a piecewise function. Constructing a rational function, and then applying that model that we find. So everything's contextual. All right, everything's about picking out what kind of function are we going to use, all right, and then the different methods we're going to use to do so. I'm going to show you some things that hopefully you will pick up on pretty quickly. That's the hope, right? So let's talk about how we could pick out a linear function. We did that earlier on in Unit 1. We were looking at a table of values. How did we know something was linear when we looked at just a table of values? The rate of change was the same. So if we're looking at a situation where it's possibly linear, we would say that there's roughly a constant rate of change. That's no different than what we've done in the past, okay? Especially if they give you a table of information and they ask you, hey, which model is this? Okay, so there will roughly be a constant rate of change. Now, when we jump to a quadratic function, it's a little more, there's just a little more stuff we can look at. We can do that second difference, remember when we did that, which basically means that we have roughly a linear rate of change. Okay, that was that second difference that we talked about. Okay. Something else that can be a clue to us is that our table is roughly symmetric. So if we're looking at those y values, some of them seem to repeat. They're symmetric around a single max or min. And we're referring to the y values when we speak of that. Okay. And then contextually, anything that addresses area is quadratic, okay? Because area has square units. Okay. So all indications that we would want to use a quadratic function. Okay. And then for cubic, we could do that, use that third difference if we had a table of values and so on and so forth. But the biggest indicator for a cubic function is in a context of volume, because volume has cubic units. So those are kind of be our indicators of what type of function we would use. Okay, take a second and look at these 3 situations, okay? We're not going to solve a problem. We just want to kind of think which of those 3 at the top would I use, a linear, a quadratic, or a cubic function in that situation. Take a second, read those, and then let's talk about them. Who won last night? Did you watch the race? We started it, but then went to bed. Do you even follow NASCAR, or you just like the shirt? God, what is it? All right, let's see what we think here. There's a lot going on in these. So the first one says balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. Okay, so what's the context of this in that last sentence? It's volume. Okay, how much water the balloon holds, that's volume. Because it's volume, we're going to use a cubic function. Okay, we use a cubic function because we're talking about volume. On the second one, Totino's Pizzas. All right. How many of y'all really like a Totino's pizza? No? Even late at night? Okay. They're my favorite. They get real crispy on the... Okay, anyway. All right. Totino's Pizza, they're the cheapest, easiest pizza. You'll live on them in college. It's okay. You can air fry those puppies. All right, anyway. Totino's Pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 and $2.19, depending on the variety. The total number of Totino's Pizzas are counted relative to the total price of the purchase. What do you think? It is linear. All right, it is linear. Okay. When we talk about why, all right, the price varies by the variety. Okay. And then finally, look at the draw, okay, if there's one of each. Sprinklers placed in a yard to water the grass. It rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler. What do you think? It is quadratic, okay? Area was our big indicator there. Okay, so looking for those clue words, things that clue me in. What type of function am I going to use to solve this problem? Okay, so let's just get into some of the nitty-gritty of it. All right, we really like cylinders and cones in pre-cal and calculus, just putting it out there. Okay, I don't know if they just like canned foods and ice cream, but that's where we are. Okay. All right, shameless plug. So, no, that's where you work. Crumble released their new cookies this week. One of them was the Tres Leches cake. So good. So good.
Milk 3.
Yep. It's good though. Okay. So here we have a right cylinder. It has a height of h that is twice the length of its diameter. Okay. So we've got this diameter. And then we've got our height. Ooh, a little geometry for y'all. Okay. So our diameter and our height. Right. It tells me that my height is twice the length of my diameter. Identify the function v of r that represents the volume of the cylinder in terms of the radius. So we don't want to do this formula in terms of a diameter or a height. We want to do it in terms of radius. So let's think for a second. Okay. My diameter is actually what? 2 times my radius. Okay. And my height is 2 times my diameter.
Wait, really?
That's what it says.
Oh, yeah.
Okay. So how would I label the height in terms of the diameter? It's 4r. Okay. 2 times 2r, which is 4r. All right. So just taking what we know about this cylinder. They even gave me, bless you, the volume formula, which is great. Okay, so now let's plug in what we know. We know H is 4R, so V is pi R squared, and H is 4R. Okay, so what's my new formula going to be?
4R cubed.
Yep, 4 pi R cubed. So which one matches? okay? Because we wanted it in terms of the radius. So just doing some substitution there, okay?
Confused on why you put the 4R in the height. I don't even know what
Because the height is
question
4R.
Part one's asking.
Because the height is 4R.
The diameter's, the height's twice the diameter. But I don't want D in my formula, I want R in my formula.
Question asking.
To rewrite the formula in terms of R. It says, identify the function that represents the volume in terms of the radius. In other words, no H's, just R's. Okay. All right, let's look at part 2. So now let's use our formula. What's a reasonable domain and range for this problem? Okay, let's think about that for a second. My domain deals with R, my radius, okay? In my formula, R controls everything, right? What's got to be true about that radius? It's got to be bigger than 0, all right? We're not going to have a negative radius. Is it going to equal 0? No, because then I don't have a cylinder if I don't have a radius. So R's got to be greater than 0, okay? What about my range? That's my volume. It too's got to do what? Be greater than 0, okay? Not a trick question, all right? If we're going to have a cylinder, then my radius has got to be bigger than 0. My volume's got to be bigger than 0. Now, is it logical to think that this cylinder will continue just to increase over time forever and ever until all of infinity? No, probably not, okay? So they're going to give us a little restriction, all right? And they tell us down here that using that formula, same one we just found, what's a reasonable domain and range for this problem if the diameter can never be larger than 20, okay? So we want to redo the domain and the range, okay? And my domain deals with R, but they didn't give me information about R. They said that the diameter can never be larger than 20, okay? Which means my diameter's got to fall between 0 and 20, okay? But my diameter is not what my domain references. What does my domain reference? The radius, okay? So, how do I get the radius from the domain? From the diameter. Yeah, okay, I got 2 of them. So then to get my radius, I'm just going to solve that inequality. Divide by 2. And so my domain, my radius has to fall between 0 and 10. Okay. So we want it to be greater than 0, but this time we're going to cap it. All right, we don't want the diameter to be bigger than 20, so our radius can't be bigger than 10.
Where'd you get the stuff from part 2? Like domain represents radius and range?
Because in my problem, my independent variable is R. My dependent variable, which would be my Y, is V. You're thinking X and Y. X is domain, Y is range. So we have to look at what's the X in the problem, what's the Y. Okay. Now for range, we've got this formula. Well, now I've got an actual value to put in there. All right. What's my volume going to fall between? Well, if I let 0 be the radius, the volume's going to be 0. Okay. But if I let the radius be 10, what's going to be my largest volume? What's 10 cubed? 1,000 times 4. We'll just call it 4,000 pi. Okay, just plug it in. All right, what's that largest X value or R value that you can plug in? Okay. So domain and range. Taking a formula, rewriting it, thinking about its domain and range in terms of a situation where it doesn't grow forever. Would not be unusual for you to see units here. So next to that range, they might have centimeters cubed. Next to domain, they might have centimeters. All right, so just as a reminder there. Okay, so manipulating a formula with other information. We do a lot of that kind of stuff, rewriting based on information we've been given. Okay. So I want to talk as we move into a rational function. All right, that was a cubic function, but as we move into a rational function, I want to talk about something called things being directly proportional and things being inversely proportional and what that means. Okay, anything that's directly proportional is linear. All right, we write that as y equals kx, probably how you've seen it in Algebra 1 and Algebra 2, but it's linear. Okay. When something is inversely proportional, all right, that's where we move into a rational function, and it's k being a constant over x, all right, so it becomes rational. And here's why that's important. When we speak of things that are directly proportional, okay, as the input increases, the output increases. Okay, so in other words, as x gets bigger, y gets bigger. Okay, input and output. Likewise, as my input decreases, my output decreases. Okay, so whatever x does, y does it too. All right, so directly proportional, they do the same thing. All right, if x gets bigger, y gets bigger. All right, if x gets smaller, y gets smaller. All right. Now, when we think about things being inversely proportional, this is where it gets a little different. Okay, so let's take a look at this one. As my input increases, right? Think about that. If I'm looking at this function, some number over a really big x, what's y getting really close to? 0. Okay, so as my input increases, my output decreases. And that's the main difference between things being directly and inversely proportional. And then vice versa, as my input decreases, my output increases. Why is that important? I'm going to show you. Yes?
What if, like, inversely, it was like a number over 1? You wouldn't have
It's going to always get closer and closer to 0. If your x value gets bigger, then your output's going to get closer to 0. Let's look at some of the problems. I think it'll help you see it a little bit. Okay. All right, here we go. So let's look at this one. I like these. It says, suppose the output of a function is inversely proportional to the square of its input. If we know one data point of the function is 1030, can we find the output for an input of 50 units? Anytime we look at a problem like this, okay, especially with things that are inversely proportional, the output, we'll call that y, is inversely proportional. That means I want a fraction and there's some number on top, okay, to the square of its input. How would I represent that? X squared, okay? In order for me to do this problem, I've got to figure out what k is, all right? What is that constant of proportionality? So this is where the ordered pair they've given me comes in so useful, all right? So they gave me the ordered pair 1030. Let's put them in the right spot. Right? If we do that, 30 goes in for y, k is what I'm looking for, and x is 10 squared. Right? We need to solve for k. Pretty simple equation at that point. Right? So that gives me 30 equals k over 100, or what would k equal? 3,000. Okay. So my actual equation that I'm going to be working with is y equals 3,000 over x squared. That's all I did to start, okay, was to find my equation. Got to know what k is so that I can analyze this next point, all right? The next thing it asks me is, can we find the output, so I want the y value, for an input of 50 units, all right? So what are we going to plug in 50 for? X, and that's all we do. So y equals 3,000 divided by 50 squared. 3,000 over 2,500. Three over 25, or 1.2. Okay, so you got to find k. Question about that? Okay, let's look at it graphically. Suppose the price per pound, P of Q, of a particular whole grain is inversely proportional to the quantity Q demanded. Which of the following graphs could represent this relationship? So we're looking for something that's inversely proportional, which means one of two things has to happen. If X increases, what does Y do? Decrease. Or if X decreases, Y increases, okay? Well, if I look at all of these functions, what's happening to every X value? It's increasing, okay? Which means the one I want is the one where the Y values decrease, all right? Which means, do they go up or do they go down? They go down. Which one's going to do that? The first one. Congratulations. Okay, so just interpreting the graph. Okay, my Y values are getting smaller as my X values get bigger. Okay. All right, try number 5. All right, let's see how we did. So it says, suppose the price per pound, P of Q, that's a Y value, is inversely proportional, so I need a K, over the quantity demanded, so that would be Q. Right? So there's the start of my equation. To write the equation, which is what it's asking me to do, I just need to find K. All right? So hopefully they've given me a point that I could plug in to help. And they have, that the price is 4 when 2,000 pounds are being demanded. So price is P of Q, so I have 4 equals K over 2,000, or what is K equal to? So my final equation, 8,000 divided by Q, and that's all it wanted. All right, so questions about proportionality, directly proportional, inversely proportional. Probably going to see inversely more than you'll see direct just because it's the rational function. Okay. All right, so let's jump into some more complicated problems. Lots of words, everybody's favorite. All right. So it says keeping it real. We just got to do some application, all right? Contextual situation. They find a way with AP to ask you lots of things in context that you'd probably never consider. One was about the feeding monkeys bananas in a zoo one year. One was about a baked potato heating up and cooling off. Like, they get really creative, all right, with there. So we're going to start with lemonade. Any lemonade fans in the house? Chick-fil-A Diet Lemonade. It's my favorite. Okay. Oop, too far. So let's take a look at this one. I'm going to kind of step you through this process a little bit. Okay. So a worker at a lemonade manufacturer prepares a machine to mix their product. A large tank currently contains 100 gallons of lemon juice into which 20 pounds of sugar have been mixed. When the worker starts the machine, a faucet will open, pouring 10 gallons per minute of lemon juice into the tank. At the same time, sugar is poured at a rate of 1 pound per minute. Okay, so we're putting lemon juice and sugar in there all at the same time. Okay, so the first thing it wants me to do is to write a polynomial function, meaning not a fraction, nothing crazy, just a polynomial function that describes the amount of lemon juice in gallons in the tank as a function of time t. So we're just talking about the juice, okay? Not the sugar, just the juice. So let's go back and look for all things sugar, okay? All things juice. So it currently contains 100 gallons of lemon juice. When they turn on the faucet, it's going to pour in at 10 gallons per minute, okay? So just the juice is going to have the equation L of T equals, okay, what did we start with? 100 gallons plus 10 gallons per minute. So that function for just the juice, L of T, is 100 plus 10T, all right, for every minute, okay? Let's do the same thing for the sugar, right? How much sugar did we start with? 20 pounds. And we're going to add it in at a rate of 1 pound per minute. So plus T or plus 1T, if you wanted to put it that way. Okay? So two linear functions there. They're just polynomials, right? We started with something. We're adding it in by minute. Okay? Now, part C takes us up a notch, and it says, hey, let C of T be the concentration in pounds per gallon of sugar the lemonade solution. We want to write an equation for the rational function C of T. Because it wants a rational function, that means it's a fraction. Okay? Rational means a fraction. But notice that language right there, and I think this is really interesting. Pounds per gallon of sugar. What was measured in pounds, the juice or the sugar? The sugar. So pounds, my sugar, per gallon, my lemon juice. Okay, so when I set it up, pounds, the sugar equation has to go on top. The lemon juice equation goes on the bottom. So I end up with 20 plus T over 100 plus 10T. Okay, that's my equation. And I did it based on the units. Right? They will always give you some kind of hint. All right, usually with units to know which equation needs to go where. All right. Question about that before we move on to the next start. Okay. So we've got our equation. Well, now let's do something with it. Right? So in part D, it says determine the concentration of the mixture after 10 minutes. What does it want me to do? Plug in 10. All right? It's not asking me to do anything miraculous. It just wants me to plug in 10 to my concentration equation. So 20 plus 10 over 100 plus 10 times 10. Okay. That would reduce to 3 over 20. We want some units here. Pounds per gallon. You could also get a decimal approximation if it was a calculator question. Okay. This very easily could be non-calculator, okay? All right, and I think the last question is probably my favorite part because it asks us to apply what we know about asymptotes and what they mean in context. So it says to determine the horizontal asymptote of the function c, okay? Remember, when we're looking at a horizontal asymptote, we're looking at the highest degree term of the numerator and the highest degree term of the denominator, okay? If they match, what's my asymptote? Yeah, it's the leading coefficients, right? That ratio. And so if we look up here, right, for my horizontal asymptote, I have a 1t over a 10t. So what does that reduce to? 1/10. So that is my horizontal asymptote. Okay, what does that mean? All right, what does that mean?
The concentration will ever be one.
Yeah, the concentration is approaching 1/10 pounds per gallon. Okay, what does a horizontal asymptote do? It's what my function approaches. Okay, so our concentration is approaching 1/10 pounds per gallon. All right. Question about that one. It's our first one with a rational function. All right, let's look at the next one. Now, the things that's crazy about application problems is, y'all, there's no way I can show you every possible application they might ask, okay? What I can do is just give you a good variety, all right? And that's what I intended to do today. So if we look at this one, a drug company estimates that to produce a new drug, it'll cost $5 million in startup resources, and that once they reach production, each gram of the new drug will cost $2,500 to make, all right? Determine a formula for the function C of Q that models the cost of producing Q grams of the drug. Are we doing anything special to make that drug? Not really. How much is it going to cost me to start? $5 million. Okay. And then it's going to cost me another $2,500 for every gram I produce. Okay. So it's a linear function. All right. So that's a lot of money. Okay. Now, they need to sell the drug at a price more than $2,500 per gram in order to at least break even. So to investigate how they might set prices, let's first consider what the average cost per gram would be. What would be the cost of just producing 1,000 grams? Well, let's see. Let's plug that in. C of 1,000. So I do 5 million. Plus 2,500 times 1,000, that'd be another what, 2.5 million? So $7.5 million. Whoosh, that's a lot of money. Okay. But what if I wanted to know now, not the total cost, but the average cost? What would I do with that total cost? Divide it by 1,000. Okay. So I take that value I just got and divide it by 1,000. Okay, so 7.5 million. We divide it by 1,000. All right, you might need all the zeros. All right, but it would give you 7,500 per gram. Okay, so we just divide it by the total number of grams. Was that terrible? No, pretty straightforward, okay? Pretty straightforward. But let's look at the next two questions, all right? The next two questions ask this: can you write an equation for the average cost to produce it? Okay, well, let's talk about what we did. We took the cost at a certain value, and then we divided it by that number of grams. And so if we want to write our average cost function, we literally just take our original equation, which was 5 million, plus 2,500. And we divided it by how many grams we put in there. Okay, that was our equation. It's what we did. Now, why are D and E the same thing? That's what it's asking me. Yeah, exactly. I just divided, right? I did just some algebraic simplification, and we divided by Q. That's the only difference. That's why they're equal, right? We divided by Q. And it is, in fact, the same equation. So you could see both of those, all right, representations, right? Now, on F, what can we say about the long-range behavior of A? What does that mean in this context? What can we say about the long-range behavior? That means the end behavior. In other words, I'm thinking about, is there a horizontal asymptote? Okay, I like our equation better because when I look at it, I can see the 2,500 Q on the top and the Q on the bottom. Are we going to have a horizontal asymptote? Yeah, we're going to have a horizontal asymptote equal to what? 2,500. Okay, is my horizontal asymptote. What does that mean? It means that my average cost approaches 2,500. Okay, that's all it means. All right, so questions on any of that I've shown you, because I think everything else is you're going to remember from Algebra 1 and Algebra 2. Good. Okay. All right, the last thing that I have for us to look at today deals with regression, using your calculator to do regression. Okay, and so I put the steps on there just to kind of walk you through it. Stat, edit. Remember, we put things in the list. Remember, if you need to clear a list, don't hit delete. If you hit delete, the list entirely disappears. All right, but to clear the list, you highlight L1 and hit clear. Go up on top of it. Okay, hit clear and then enter. Okay, so enter's kind of like your say please button. All right, clear and enter. If you hit delete, it disappears. Okay, and if you ever make it disappear accidentally, if you look right here on this first edit menu where it says set up editor, if you go in there and hit that and then enter again, it'll bring back list 1, 2, 3, 4 to see. Okay, so that allows you to reset, just as a hint. Okay. We're going to actually walk through and do one here in just a second, but I just wanted to show you the keystrokes again. Then it talks about how to get your regressions. There's lots of different regressions to choose from. StatCalc is the menu you use. Have you ever noticed that there are two linear regressions, AX plus B, A plus BX? Okay. 8 is what we use in statistics. I don't know why. They put the y-intercept first, and then the slope and the rate of, the slope and the x value. They will give you the same equation, all right, regardless of which one you choose. But just be careful. If you use the first one, the first number goes by the slope, then the y-intercept. If you use the number 8, y-intercept first, then the slope, all right? So just don't write them down in the wrong place, all right, for what you're used to. When it comes up, you'll choose which regression you want. It's really important that you store that regression equation in Y1, and I'm going to show you why in just a second. To store it in Y1, alpha trace, all right? And that's a shortcut button you've probably not used before, but alpha trace, you can store that equation in Y1, and then it's automatically there, and I don't have to type it in. So I don't make rounding errors, and I don't mess it up. Okay? So doing regression. lots of times it will tell you which equation to use. Other times it will want you to guess based on the data, all right, in the chart. So we would need to investigate to see, should I use linear, should I use quadratic, should I use cubic, something like that. But most times they're going to tell you. We will do regressions of all kinds all the way through trig. Okay, so we do regressions. All right, so let's do one together. Pull this up. I'm going to pull my calculator app up. Okay, now one of the things that I want to highlight for you, if you look in here, so we're talking about the age in weeks and the weight in kilograms of 5 randomly selected babies. Okay, notice right here, it says a linear regression y equals a plus bx. So it wants me to choose number 8. Okay, so it's telling me the form to use here in just a second. Okay, all right, so let's jump over. This is going to shut my recording off while I do all the calculator steps, okay? And then we'll come back, all right? So let's jump over here. It would look like this. Our linear regression model, notice it says y equals, we always want to be sure we put that, all right? 3, perfect Nugan. .545 plus 0.185, and we've got t. Okay. Now, part B is where we can use our calculator to help us the most. All right. So it says, using the linear model from part A, what's the predicted weight in kilograms of a baby that's 10 weeks old? Is that 10 weeks a weight or an age? Age. So 10's going to go in for T. Now, I want to use my calculator for the second one. Okay. So we would get that our weight at 10 weeks was 5.395, and we'd put kilograms. Okay. But notice how the third question's a little bit different. This time it tells me that the weight of the 6th baby is 5.3. Okay. In other words, I want to figure out what's T. Okay. So a little different type of question. Okay. When that happens, we're going to take and put that value in Y2 and look for an intersection. Where do those two graphs cross each other? Okay. If I have a Y value, which is my weight of 5.3, what would be the age of my baby? Okay. Again, it's linear. That would be easy to solve by hand. Okay. You'd put it in for Y and solve, right? But our calculator will do it all for us and keep all of our precision. So why not let it? Okay. So I'm going to go back to my, so, all right, you're looking for an intersection to find that T value. Okay, so my time would be about 9.486 weeks.
Mine doesn't do the internet.
Do you?
It says left down and then right
Oh,
down.
that might be new, one of the new programs. Okay, all right, so here's what I want you to do for me. Okay, I've given you lots of different things to practice. Okay, the AP questions are really good. They're going to challenge you. All right, the worksheet A, it's not too terrible. It's just basically there's 2 problems on there because I want you to practice using your calculator. All right, so on worksheet A, we're just going to do problems 1 and 3. Okay. Then you've got the AP practice for 1.13. There's 4 problems. I want you to do all of those. They're multiple choice. And the AP practice 1.4. Now, how can you tell all of those? There's 4 of those as well. Okay. How can you tell that on the AP practice, if it's a calculator question, it'll have a calculator next to it? Okay, so we'll have a little calculator symbol. That's how they indicate those on AP Classroom. So calculator symbol implies calculator. Okay, be sure and practice the one, I think it's number 3 on the worksheet A that uses the calculator to do your regression. If you need to do that right now before you leave so I can help you navigate those steps, let's do that right now. Okay? Yeah.
These are the last things you're learning for the test.
Yes. That was it.
Just like
Tomorrow's review day. I've made you a study guide, and your progress check will open on tomorrow morning on AP Classroom. It's 24 questions. It's good. All right, it's really good. It's probably stronger than the study guide, if I'm just completely honest. Not all those questions, but it's got really good questions on it. Okay, and then and your study guide, I think, has 12 questions on it. The test is 15 multiple choice and then 1 free response. Okay, 13 are non-calculator, 2 are calculator. All right, that will eventually even out, not even out, but you'll get like 5 that are calculator. Okay, but we're just not there yet. So, okay.